Hi there. So in this video we are going to see the laminar flow through the pipe. We are going to build the geometry, then we will do the meshing, then we will set up physics, and then we will see the post-processing. In that we will see the velocity profile, pressure distribution, streamlines and particle movement. So welcome to this channel Unleash Fluid Flow. How to identify whether the flow is laminar or turbulent in the pipe? For that we have Reynolds number. The Reynolds number is rho V divided by mu. So rho is density, V is velocity, D is hydraulic diameter, mu is dynamic viscosity. And if Reynolds number is less, then the flow is laminar. For a pipe flow, the critical Reynolds number is 2000. So if Reynolds number is less than 2000, then the flow is laminar. If Reynolds number is more than 4000, then the flow is turbulent. So for that we are considering one pipe having the length L and inner diameter is capital D. So we are considering the specification like this. Inner diameter is 40 mm, length is 1000 mm, that is 1 meter. Velocity from one end, it is 0.005 meter per second. And fluid we are considering as water having property like density 1000 kg per meter cube and dynamic viscosity 0.001 Pascal second. So for this case, our Reynolds number is 200. So for that, we'll see the laminar flow through the pipe. So there is one concept of entrance length. So you can see in this image, this one is entrance length, and within this entrance length, the flow is not fully developed. It is a developing flow, and after this entrance length, the flow is fully developed. That means the velocity profile is parabolic after in the fully developed region. Now in our case, this is our pipe and our entrance length is this one. So in our case the entrance length is 0.4 meter. So up to 0.4 meter our region is developing region, and after that it is a fully developed region. So after that, if I consider any section, for that section we can draw the velocity profile, and that velocity profile will be the parabolic. So if I draw the velocity profile here, it will be parabolic. Now in the developing region it is not parabolic. If I consider the inlet section, the velocity profile is like this. So let's try to see the same thing by using Ansys Workbench. Open Ansys Workbench, click on this Fluid Flow Fluent, or you can drag this. Then double click on geometry or right click on the geometry and go to the new design modeler geometry. So first set the units, click on units, then millimeter, then XY plane, go to the sketching, select a circle and draw a circle with some radius. Likewise draw another circle, and then you can go to the dimensions and you can choose the diameters. Like for this outer circle, diameter is, let us consider 50 mm, and for the inner circle diameter is 40 mm. In our calculations we have considered inner circle diameter as 40 mm, so that's why I consider 40 mm. Then extrude this, select this sketch, click on apply, and you have to enter extrude length, so that is 1000 mm. Then click on generate and you can see the isometric view. Just click on zoom to fit. So this is the solid outer body. Now we have to create the inner fluid region as well. For that, go to the tools, click on fill and select the inner section. So you can see the inner section is highlighted. Then click on apply, then click on fill and click on generate. So the fluid region will be generated. So you can see here two parts are there. One part is this solid outer part and second part is this inner part. So just rename this inner part. You can rename this as fluid. Then close it and double click on mesh. Okay, so here we are going to do the meshing. Also we are going to name some parts. So click on mesh and directly click on generate. So default mesh is generated. You can reduce the size. So I'm going to reduce the size as element size as 5 mm. Then again click on generate, or you can click on update. Okay, so that's my mesh structure. We can see the statistics also. So how many nodes are there, how many elements are there, that we can see. Then we have to set the names. So I'm considering this surface as inlet section. So, and similarly, this surface will be my outer surface. So again, I'm going to select the surface, right click on that, click on create name selection, and this boundary is solid boundary. So click on that. You can see it is a solid boundary. Again, right click on that, go to the create name selection, and you can put like solid underscore wall. So that's all. We can see these names here. So this is my inlet section, this is my outlet section, and this is my solid wall. Then we can close this, and here you can see one flash mark is there. That indicate that this is not yet updated. So you can click on update project, or directly right click on this and click on update. Okay, so mesh is updated. So double click on setup. It is automatically 3D because we have drawn our pipe in 3D. You can click on this double precision as well to get the better results. Click on start. Initially you may get several windows like this. Just click on allow access. Okay, so this mesh structure is loaded in this Fluent. So you can see the scale. So scale also you can see X maximum and minimum distance. And you can change this scale also. So like if I click on mm, then my X is around 25 mm to 25 mm. Since my outer diameter is 50 mm, that's why. So likewise Z also you can see 0 to 1000 mm. I'm going to convert this into meter only. Then you can check this mesh. So mesh also you can check. You can report the quality of this mesh. So you can see the orthogonal quality, aspect ratio, these things you can see here. Likewise you can display it, you can set the units also. In our case we are going to use the pressure based solver, and it is steady state condition only. So I'm keeping as it is. Then go to the model, then go to the viscous and click on laminar, then OK. Then in the materials, go to the materials, then in fluid you can see only air is there. By default the fluid air is there, and in the solids aluminum is there. Now if you want to add another fluid, just double click on this air. Then you can go to the Fluent database. So here different different fluids are there. So out of that we want water liquid. So click on water liquid. So these are the properties of this water liquid. You can edit this also. Click on copy, then click on clothes. Here also you can click on clothes. So you can see water liquid is added. Likewise you can add different fluids. In the solids also you can add different solids in the similar way, but I am going to keep my outer body as aluminum solid body and fluid as water liquid. Then click on safe zone conditions, and the fluid section we have to assign this fluid as water liquid. So just double click on this. So here you can see by default it is air, so we have to change this as water liquid. Then click on apply. Likewise in solid also you can do that, but hence since we are going to keep aluminum only, so by default it is aluminum. You can check that also. So here you can see only aluminum is there. If you added any other material, you can fuse that also by using this tab. Then go to the boundary conditions. Double click on this boundary condition. So you can see these different conditions are there. Out of that we have set this inlet, outlet and wall, that is solid wall. Then click on inlet and click on edit. So we are going to set the velocity by using this. So our inlet velocity is 0.005. 0.005. This is in terms of meter per second, you can see, and it is normal to the boundary. So you can see it is normal to the boundary. So just click on apply, then click on close. Then we can check the outlet. Outlet should be pressure outlet. Okay, so outer pressure is atmospheric pressure. In terms of gauge pressure, it is 0. You can see this. Then click on apply, then close. Then we can see this solid wall. So it should be wall. So it should be stationary. That also you can check. So you can see it is a solid wall only. So it is a stationary. We don't have to give anything. So these are our boundary conditions. Now we can check the monitors also, residual monitors. So we have continuity, x velocity, y velocity and z velocity in the residual monitors, and these are our criteria. Then go to the initialization, click on standard initialization and compute from inlet. Then click on initialize. Then go to the run calculations, and here you have to give the number of iterations. Now I am giving the number of iterations as 2000. If my solution is converged within these 2000 iterations, then I will get the pop-up window as solution is complete. If it is not converged to the 2000 iterations, then after the 2000 iteration it will be stopped. So I am going to click on calculate. You can see iterations are going on. Actually, it is depend on how much your mesh size is there. If your mesh structure is very much fine, then it may take certain time. If your mesh structure is little bit coarse, then it may not get that much amount of time. But again, accuracy is also important. If your mesh structure is very much fine, the accuracy will be the better. Now my solution is converged, I guess, within 45 iterations. So I guess my mesh structure is little bit coarse. So my solution is converged within this 45 iterations. Click on OK. Then we can see the post processing by using this results window also, and by using other post processing application from the Ansys. So I am going to use that. So here setup and solution, these two things are over. Now we are going to see the results. In order to see the results, we are going to use the CFD post processing. Just double click on this result. Okay, so our solution is loaded in the CFD post processing. Then if you want to see this fluid layers like inlet, this is our inlet section. Then outlet, this is our outlet section. Then you can see the two contact regions as created. This is contact region target, that is fluid region, and for the solid wall it is contact region SRC. So you can click on that, so you can see that fluid region, and the same region is there for the solid, and you can see the solid wall also. So this is just in order to see this pipe structure. Then we want to plot the velocity vectors. So for that we need the plane. So I am creating one plane. So plane 1 I am creating like it is YZ plane, and it should be at the center. So that plane I am creating. So that is my plane number 1. That is my YZ plane. So I am going to plot the velocity vectors on this YZ plane. So click on vector, and for the all domains, location is my plane 1. Also you can see your velocity vectors at inlet, outlet, everywhere, but I am going to plot the velocity vectors for this plane 1, and just click on apply. Since everything is visible, so that's why we are not able to see that velocity vectors carefully. So just uncheck this these things like contact region, inlet, outlet, contact region of the solid, and outer solid wall. So you can see this velocity vectors. You can see the 2D view. Just click on this x-axis. You can see this 2D view. You can zoom it. So for the zooming, you can use this tab. So at any section, you can zoom it, and you can see this velocity vectors. You can see this velocity vectors. You can use the scroller also. to zoom or unzoom it, or you can use the fit window also. Here you can observe maximum velocity is at the center, and its value also you can see. That value also you can get from this color. You can see this maximum value. So minimum value is this one, and that is approximately equal to 0.0017, and maximum value is 0.0097, that is at the center. So likewise you can plot this velocity vector for the inlet section also. So I'm going to plot this for velocity vectors for the inlet section. So in the inlet section it is developing region, so we are not able to see any parabolic velocity profile. So velocity is uniform at the inlet section. Likewise we can see this velocity profile at the outlet section also. And there you can see the parabolic profile. So just choose outlet and click on apply, and we have to move towards outlet section. So just click on zoom, and this is my outlet section. So you can see it's a parabola, near the parabola. At the center the velocity is maximum, and near to the surface the velocity is nearly 0. Now we can choose the plane at any of the point, any of the location. So I'm going to draw my plane nearly at this location, so I can see the parabolic velocity profile at this section also. Now for that I have to create one more plane. So just click on plane, that is plane number 2, and that plane should be XY plane. It should be XY plane. Its location from this point, from the Z, that is 0, 0, I am keeping this as 0.1, 0.1, sorry, 0.1 meter. Then click on apply. So you can see one more plane is created. Now I'm going to plot my velocity vector for that plane. So here my vector 1 is there. Just double click on that, and in the location just click on plane 2. Okay. Now I'm going to turn off this plane 1 and click on apply. Sorry, it should be plane 2, then click on apply. Okay. So you can see this velocity profile at this section. Likewise you can plot the velocity profile at any location. Now similarly we can see the pressure regions also. So pressure distribution, for that I am going to click on contours, and we are interested in pressure region. So for that I am considering the location as contact region TRG, that is fluid region of the outer near to the pipe surface, and we want the pressure. So just click on apply. So we can see this pressure. So just I am going to switch off this plane 2 also. So this is my pressure distribution. 2D view, you can see this. So at the starting point pressure is very high, that is 1.168 something, nothing to 10 raised to -1. As the water is going through the pipe, the pressure goes on reducing, and the least pressure you can see at the outlet section. Now we'll try to plot the streamlines. So just click on the streamline. I am going to uncheck this contours, and we want the streamline for the entire domain, and it should be start from inlet section. Just click on apply. So you can see this streamlines in the isometric way also. I'm going to uncheck this plane number 1. So these are my streamlines. You can see the streamlines are exactly parallel. Then we can see the how the particles are moving. Just click on animation and click on streamline 1 and just click on play button. So you can see how the particles are moving. Now that it is moving a little bit fast, so you can reduce the speed. So you can observe the particles which are at the center is moving with some higher velocity, and particles which are near to the periphery is moving with very low velocity. So this thing you can observe from the streamlines, and you can also see how the particles are moving. So that's all from this video. Thank you.